Hi, I'm going to present our work on robust task-based grasping as a service, in which we will formulate a novel and intuitive way to specify a task that enables automated computation of a robust grasp for that task. I will also present how we made a web-based service for it that allows anyone to use it. Task-based grasping considers the task when computing a grasp. For example, on the left, we need to grasp a draw by the handle in order to use it. On the right, the person passing the baton needs to leave the room for the other person to grasp it. If you were just to consider how to optimize the grasp to pick up the object, as many grasp analysis algorithms do, the resulting grasp might not be able to perform the task. Task-based grasping is important in many contexts, including automation of assembly. For each step of assembly, different grasps are required based on how parts fit together. The same object may require different grasps from one step to the next. Task-based grasp computing is important for many real-life and automation applications. One question we aim to answer is how to specify a task intuitively. One thing we consider is that tasks usually have restricted contact areas. For example, we grab credit cards differently depending on the scenario. To hand the card over, we need to leave an area for the cashier to grab it. To insert card into a chip reader, we need to grab on the edge of the card so that we can push it in. To swipe the card, we cannot touch the magnetic stripe region. And to tap the card, we need to leave enough area free for the machine to read it. With this in mind, we introduce the concept of task-specific stay-out regions. In addition to stay-out regions, we also need to consider task-specific forces and torques. For example, to use a knife to cut, the grasp needs to be able to apply a force. And to use a wrench, the grasp needs to be able to provide a torque. With this in mind, we also introduce the concept of task-specific forces and torques. Prior research has also investigated grasping strategies applying external task wrench, and some recent works has focused on using environmental information about the planned trajectory to plan grasps. There is also some related work that looks at data-driven strategies to learn task-based grasping strategies. In this work, we extend the grasp analysis algorithm from DexNet to add task-based grasping. We also extend DexNet as a service to develop a cloud-based public API for computing robust task-based grasps with parallel jaw grippers on user-specified meshes. In this work, we address the following problem. First, what are constraints required to define a task? Second, how to specify the task constraints in object geometry. Third, how to generate robust grasps given the task constraints. Our proposed approach includes, first, a task-based grasping model using a mesh augmented with stay-out zones and task wrench. Second, an intuitive task-based grasping user interface that takes input as 3D object mesh and allows non-specialists to indicate task constraints with stay-out zones and desired wrenches. Third, a grasping planning algorithm to compute robust grasps based on the task-based grasping model. We define the task-based grasping model by first identifying the stay-out zones. To define the stay-out zone, we paint the faces of a mesh. Here, the dark red region is painted as the stay-out zone for using a screwdriver. The grasp planning algorithm will ensure that computed grasps do not touch these areas. Also in the task-based grasping model, we define the external force and torque needed for the task. Here, the blue arrow pointing down is the task-specific force, and the red circle arrow is the task-specific torque. As part of this project, we developed a user interface to specify a task-based grasp model and made it available online at dexnet.app. On the left, we can see a preloaded object mesh, its associated grasps without task constraints, and the parallel jaw gripper. Each computed grasp is displayed as a whisker that shows the contact points as well as a color-coded robustness measure, where green means most robust grasp and red means the least robust grasp. On the interface, we can upload meshes to compute grasps on new objects. To do so, we select Choose Object on the right and upload the screwdriver mesh. Afterwards, we can pin the stay-out zones by holding down Ctrl and dragging the mouse over the object surface. To specify the wrench, we click on the point that we want to apply the force on. The force and torque are drawn automatically. We can adjust the magnitude of force and torque by moving the slider. We can also adjust the width of the gripper as it can vary from robot to robot. Now it's ready to compute the task-based grasp. The user interface that I just demonstrated is the front end of the task-based grasping as a service system. The actual analysis takes place in the backend. When user clicks on the Compute Grasp button, it sends an HTTP request from the web browser to the backend through a Python-based Flex API. The backend analyzes the model using the algorithm that I will present in next slide. It then returns the grasp analysis results to be displayed by the front end. The grasp planning algorithm takes mesh object, gripper object, stay-out region mout, and external wrench tau that includes force and torque. The algorithm starts by sampling candidate contact points on the object mesh, and discards any point that contacts a stay-out zone. It then should race from the point in random direction within the friction cone until it intersects with the other side of the mesh to create an antipodal contact point pair. These 2 points define the candidate grasp. The algorithm then prunes the candidate grasps that collide with the gripper. If the gripper is wide enough to grasp on the mesh, and if the antipodal point falls outside the stay-out region, we add grasp G to the list of grasp candidates. If one of the answers is no, the algorithm continues sampling grasp candidates until it finds a specified number of grasps or reaches a fixed sampling limit. The algorithm then evaluates each grasp for their robustness in resisting the specified external wrench. After user click on Compute Grasps, in the UI now, we can see the grasps generated. The grasps in the stay-out region are filtered out, and the most robust grasps, represented by the whiskers in green color, are along the direction of the rotation with the torque. We experiment to test the effectiveness of interface, grasping algorithm, and grasping analysis. We experiment with various tasks on spray bottle, tweezer, and wrench. We test the effect of specifying stay-out zone on grasp filtering, the effect of external wrench on grasp quality, and also the combined effect of them on generating robust task-based grasps. We also experiment with applications in household and industry on key and assembly objects. Here, we show the effect of stay-out zone with a spray bottle. On the left, we can see the grasp generated when there is no task specified. On the right, there's a demonstration of grasping a spray bottle to lift it up. With the lifting task, we specify a stay-out area on top and on the sides of the bottle. Then the grasp analysis can generate robust grasps in desired contact location. To pack the bottle into a box, we mark the stay-out zones on areas that will be in the box. This results in grasps at the top of the bottle. To place the spray bottle on a shelf, we mask out areas except the region on the neck of the bottle, since we want to avoid collisions between gripper and the shelf. To spray the bottle, we limit the visible region to be the trigger and the back of the cap only. To rotate the nozzle in order to turn it on or off, we would like the grasp to be only on the nozzle. Similarly, to open the bottle, the grasp needs to be on the cap only. Next, I will show examples of the external wrench on grasp quality. Here, to rotate the spray bottle, we specify a counterclockwise torque on the object. This results in grasps farther from the point of rotation being ranked as more robust, which matches with how human would likely grasp it in real life. On the right, we rotate the spray bottle around the different axes with a different torque. The grasp analysis changes to align with the direction of the rotation. Here the task is to push the bottle, so we specify a force without torque. We can see that The grasp along the direction of force and close to the point of application are preferred. On the right, the task is to push the bottle in a different direction. So we draw a different force and the result of a grasp analysis follow the direction of the force. In this example, we combine stay-out zones and external wrench. On the left, it shows the grasp generated when there is no task specified for a tweezer object. But to use tweezers, we mask the stay-out zones near the tip, and the system filters out the grasp there. To exert some force, we add the desired force represented by the blue arrow, and the system then re-ranks the quality of the grasps. In this example, we consider a wrench tool. With no task specified, there are a lot of available grasps. After we specify the stay-out zones and the torque needed to turn the wrench, the grasp analysis computes that grasps that are parallel to the torque direction are more robust. Here are some examples on a key with different task models and the resulting grasps. Rankings are on the left. 0 means least robust and 1 means most robust. To place a key on a flat surface, we mask out the top and bottom area of the key. This avoids grasps in which the gripper will collide with the surface. To hang the key on a hook, we mask out the top region of the head. So the grasps generated are from the blade. To turn the key in a lock, we mask out the blade area and add a torque indicating the desired rotation. The last task we consider for a key is cutting the tape on a cardboard box. We also show examples on an assembly task shown in this exploded assembly diagram. Each row of the table shows a single object in the assembly task. The first column shows the object mesh without any task specified. The second column shows the computed grasps. The third column shows the stay-out zones and wrenches needed for the assembly. The fourth column shows the grasp generated based on the model in the third column. With the complete system, we show examples of robust task-based grasping on a Yumi robot. In this scenario, the robot grasps a pawn to avoid collision with other pieces on a chessboard. In this task, we show a snapshot of mallet with torque constraints. In conclusion, we propose an intuitive task-based grasping interface that uses stay-out zones and external forces and torques. We also propose a grasp planning algorithm to compute robust grasps consistent with task constraints. We also experimented with a variety of objects and tasks in household and industrial environments. In future work, we would like to extend to section-based and multi-finger grippers, and also to multilateral manipulation with 2 or more grippers. I hope you all enjoyed the presentation. Please try the web service at dexnet.app. Feel free to contact us if you have any thoughts and feedback. We always welcome ideas for collaboration. Thank you so much.